All right, this next one, you want to try on your own, come back and check your solution here. Real similar to what we just did. So hopefully you could apply that moment dt, right? Take the integral of that dt. That would be your impulse term. And then we'll start again from rest and end at 4 seconds. See if you can figure out what the velocity of the spheres would be. Now there's four of them. Okay, so our initial angular momentum is going to be zero starting from rest. The final angular momentum would be four because of the four balls times the mass times the velocity times the distance to the middle, which is the 0.6 feet. Make sure you don't use 5 pounds. You got to get that into mass slugs, right? Then our angular impulse is the only term missing out of the equation before we could solve for V2. So the angular impulse, there is no forces, or there are no forces pushing on the balls this time, like there was for example one. So for this one, we only have the applied moment dt that we'll need to do for our impulse term. So the integral of that dt, we'll end up dividing that by 2, and the t becomes squared, and then we get a t on our 0.8. Evaluate that from 0 to 4, and you get 7.2 pound-feet seconds. Some interesting units there. Same as the units we'd get here. And we put all that together. Start with 0, add the 7.2, you end with 0.3727 V2 with this simplified and plugged in. And that'll get you 19.4 feet per second. So hopefully you got that. Real similar to the example, and pretty classic application there. Here's a real life application, by the way. Saw this and thought of dynamics. Wow, look at that. You could spin that thing around. You could change the radius from the outside, right, as the angular uh, velocity changed, right? The other interesting thing, if you're playing on one of these, right, it'll go if you don't apply any forces to it, it'll be going slower when the people are further out, and it'll go faster when the people are falling back in. To a certain point, right? It'll obviously slow down from friction eventually and stop. Think about this one. If the ball is going around on this smooth surface while it's getting pulled in with this 2 feet per second radial chord force, what could you use to solve for the velocity of the ball when r equals 2 feet? Well, yeah, conservation of angular momentum would do it, right? That's the nice thing is we could just take its MVD starting and its MVD final, and the change, there wouldn't be any actual applied moments, right? But its radius is changing, so its angular momentum would be changing, which changes its v, its actual velocity. Kind of interesting. If a particle moves in the zy plane, its angular momentum vector is in the x, the y, the z, or the zy direction. Yeah, and this it goes back to your cross product, right? If you're doing a cross product in the zy, then perpendicular to both of those would be the x. That would be the direction of your angular momentum vector. All right. We'll come back and do one that's like the homework to help you out with that. And that'll be it for today.